All right, good morning. Has everybody turned in their exam?
Yes.
All right. Everyone who's here has turned in their exam. That's everyone -2. Okay, so we last class we started talking about SPICE simulation, and we so here's kind of what we went over. We went over the 4 types of simulators. We talked about the background of what SPICE is, kind of the background of how it kind of emerged from SPICE decks. And when you kind of imagine, now that you know how the output files are written to the result, let me show you what I mean. So remember this right here, this graph? You can actually kind of, if you figure out how to simulate it, you can actually use a SPICE deck to kind of, it could actually generate those kind of results. So the first thing we did was we did a RC circuit. We learned how to do piecewise linear and pulse voltage sources. Showed you some fundamentals on how to write a quality file header. What option.post. When you do an option.post, what's the first thing you should do before anything else? .end at the end of the file, or else it won't run. Then for a voltage source, you have to positive voltage source, negative voltage source type of input signal, timing requirements for that input signal. We actually did this. We did an example. We figured out how to actually do a pulse. Gave an example where you take some sort of input and convert it to SPICE code. So then we learned a transient analysis. And we learned plot and how those work and how you actually use those to actually generate some sort of output waveform. And since this is an RC circuit with an expected RC transient response, this is what our circuit actually shows. We have a step input, and then we have a response on your output. So now we review the code. We now know that if you're doing something, especially with MOSFETs, which we're using in this course, RC step response for RC delay models, diodes, voltage sources. We learned about this odd concept of DC analysis. So a lot of the DC analysis we're going to be learning more about simulation models are based off of these equations, where we know that our gate source threshold voltage, drain source, or beta ratios, we can use those to actually present those IV curves that we learned about in section 2. And those are generated, we have our VGS. What's the name of the command that we can use? So we have VDS, and then we have some command that I'm asking for, and then we have an initial function. I'll give you a hint. If you're playing in the World Series and you win all 4 games, what have you done? Sweep, right? Right? We've not. We might be we might be struggling with CMOS, but we know baseball, right? So we know that .include. You include a technology file, and I uploaded a bunch of those to Blackboard that you can take a look over. You have .include. You can actually use those to simulate your file. We're going to learn a little bit about what all this means. Most of these is underlying physics, but we have some capacitance values. We have initial threshold voltage. We're going to learn about K values. We're going to be learning about, so that's we're going to use KB to relate beta and our mobility functions. We'll discuss this later in lecture today. So we have a number of capacitance values. And so the key detail that you need to know at this stage is that the model is called CMOS-N here. So if you call it NMOS in your SPICE file, you'll get some sort of error saying that there's nothing there. Same thing, CMOS-P. So you can include option.post, include, temperature 25 degrees for Celsius, and you end. And so we had the notation, we have M, you can call it N0 for NMOS. You have drain, gate, source, body, and then type. So this here we would have CMOS N. Yes?
Is this going to be the one that's due on Thursday?
No. Well, I'll talk about due stuff later in the lecture. Okay. So this is the example of what writing everything up. So here we had drain gate, ground, and ground. We tie the body to ground unless we want to study body biasing. Since it's lambda, lambda over 2 is going to be 45 nanometers, 90 nanometers, 90 and 180. So for 45 nanometer circuit, that's what we're going to do. This is our sweep command. Sweep, we've won the baseball. And we have our initial VGS and VDS. So every step, we're going to analyze 0, and then we're going to step 0.2 up through 1. So it's 0 to 1, the steps of 0.5. So 0, 0.5, 1, 1.5, 2, 2.5, all the way up to 9, 9.5, 1, and then we end 0. Then we start again, 0.2, and so forth. And so this is the complete SPICE file that we have written. We have our 2 supply source voltages that we discussed in the problem. We have our MOSFET. We have our DC sweep. And so this is what's going to happen. It starts out with 0, 0.4, 0.2, 0.4, 0.6, 0.8, and 1.0. So this is the sweep for VDS as with respect to IDS, where we have our initial input function. So now we have an inverter. So this is where we're going to start talking about concepts like .param. Parameter, we can set our supply to 1.0. We define .param as including a fixed variable value. So here, if we're trying to do supply, this means we're just going to do the supply voltage. And typically, well, not always, but typically you'd want to put your .params in uppercase just to differentiate them in your code. We also have the scale option. The scale option allows us to indicate the width and length of a transistor with respect to a set value. So here, remember back in section 1, we talked about these design rule checks. And we had our 6 rules that lambda is equal to half of the feature size, therefore the polysilicon's 2 lambda. Metal and diffusion have to be spaced by a certain amount. The polysilicon diffusion by 2 lambda is where a transistor desired has a spacing of 1 lambda where no transistor is desired, so forth, and all the way down to n-well. So here, we can set option.scale to 45 nanometers. And the reason we do this is because now this is how everything's met. So the way it's going to work when you get into when you want to actually compile your layout, what's going to happen is you're going to initially start with your polygons, right? So you have some sort of input and output. And then what's going to happen, the first thing it's going to do is it's going to check these rules to make sure you've laid it out properly. Right? And then what's going to happen next is based on this, it's going to convert it to SPICE. It's actually going to generate a SPICE file. And you're going to do this in these labs that are coming up. You're actually going to do a layout. It'll generate the SPICE for you. Then you're going to simulate the waveform. And based on the simulated waveform, you're going to see how your circuit actually works. So what's going to happen is when you define this .scale and you define your parameters, so you have VDD is the name of the voltage, and you have 2 nodes, VDD and ground. And this allows you to say that the difference between node VDD and node ground is represented by a voltage with uppercase VDD, and that is represented by 1 volt. So here's how we actually create this using a supply voltage and some sort of simulation voltage. So we're doing an inverter, right? and the ratio is 8 to 4. If you recall, it's 2 to 1, right, for PMOS to NMOS. And so we also define that the ratio of the NMOS width to length is 2 to 1. So here it becomes, length is equal to 2, and the reason why length is equal to 2, if we go back up here, polysilicon must be 2 lambda. So we've set our option dot scale to 45 nanometers. We say L is equal to 2. That means it's 2 times this. Then we have our width is going to be 4 times that. So now we've done our proper NMOS. And we know that the beta is approximately equal to this. So we're going to have our length is equal to 2 and our width is equal to 8. So going back to the code, this is how we got these widths. So the next step is how do we actually get the rest of it? So we have our PMOS and NMOS in our invert input, right? So what's commonly done is this type of drawing. What I've done here is I have a drawing to the base, to the body of the transistor, I mean. So what's going to happen is you're going to have MPO, and then we're going to call this output Y. That's our drain. Our gate is going to be A, which is our input, and the source is VDD. But if we tie the body to VDD as well, that's why we have this here. So let me get rid of all that, zoom in. So for the PMOS, drain is output, gate is input, source is VDD, and we've also tied the body to VDD. And in the technology file, we define CMOS P as our defining. So what's going to happen if we use the dot include in this, we have now included everything from that file as part of your SPICE deck. And then we have this area source, perimeter source, area drain, perimeter drain values that we discussed last lecture. For NMOS, we're going to tie the body to ground. So we have our drain, same thing as our output, inputs. Source is ground because the NMOS tied to ground, right? And then output is Y, and this is A. CMOS N, and then we've calculated our values there. And last thing we do here is we generate a transient response. So let's say we want to do 80 picoseconds. And this is going to measure it every 0.1 picoseconds, right? So this is going to end up having 800 measurements. So for 800 time slices, if you recall earlier, we were talking about that very simple example with the RC. Now we're going to have a much larger transient file. And it's going to be comparing the voltage at A, the voltage at Y, and anything else you ask for. We're going to discuss how we can measure currents and rise and fall times later today. So let's go over this last segment of code. So this is the whole code. We have our description. We have our file that we've included. We have done dot post, so first thing we do is end it with end. We have our temperature, since we're simulating at room temperature, 25 degrees Celsius. And then we have set our option scale to 45 nanometers, because that was what we were defining as lambda. We have our input voltage supply. We have set VDD as 1 volt. Here we actually have defined a pulse. Remember, we have our 50 picosecond delay. We have our 0 picosecond rise and fall times. And then we have 100 picoseconds high, and then the total cycle is 200 picoseconds. Now, then we have our MOSFETs, and then we have our transient response. For those of you who remember from last class, what's the problem that we encountered as a result of this specific input voltage waveform? So we have an inverter, and we had spikes, right? Why did we have spikes?
Because it instantly jumped up.
Mm-hmm. And what's physically going on? So this is a good combining concept. We've gone immediately from 0 to 1, and we had, so we have our condition, right? Where the input goes immediately from 0 to 1. That means, and we have an inverter, so what does that mean on the output?
Just from 1 to 0.
1 to 0, but what's happening the moment, so we have our delay, right? And then what's going to start happening? If we haven't accounted for the delay, so here's the physical. So if we have a 1, right? So what is physically happening in the inverter when we have a logic value 1?
It's turn on the PMOS, turn off the NMOS.
Right, so this is on. So what's physically going on when they're on and they're off?
The channel's created.
Yeah, we have our channel created here, and the channel is cut off here. So what's happened is we immediately spike to the opposing condition that's still high. So we have an instance where this is turning on, it's still on, but it's trying to turn off, and this is trying to turn on. And if you don't regulate that properly, what's happening is what you should be doing is you should have some sort of step response, giving it that opportunity so you're not creating that extra channel of current. By doing that, that's if you create an instance where you're going through both channels, that's where you're going to get these really high power spikes. And so when we actually show the simulation, that's what's actually going on here. The input goes immediately from 0 to 1, and your output says, whoa, 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 not cool, not cool, not cool, too fast, right? And then comes down to 0 eventually, right? And you have fall time and fault delay. And then same thing. Here, we've got again, it's coming along here, and then we have our input switches immediately to 0, right? Same thing, like, whoa, whoa, this is not cool, and then it eventually corrects over time. So this is where understanding the physics comes into play. I wasn't just doing that to torture you guys, because you understand now that we have created an overflow of current here that's flowing to the ground. Here it's flowing to VDD, so you're creating a higher output spike. Here it's flowing away, so we're actually getting negative voltage. We've now created an instance where the circuit is flowing in the opposite direction of what we want, which is why we have to account for these rise time and fall time delays. Okay. Does anybody have any questions before I continue? All right. So here we have a fan out of 4 inverter. So we have a bunch of different sizes. We have these 2 inputs. Remember, we could potentially have spikes, so we have 2 inverters here to try to buffer it, to try to shape the input the way we want. Then we have our device under test, so our test values are node C and node D. And then we have a load. Remember, everything's driven off of a load, so we have to account for load capacitance. And then finally, we have our load on load. So the question becomes, how do we do this in a more simple manner? Because before, we are defining all of our inverters, but all of the inverters are defined to a specific size, right? So what we're going to do is we're going to find something called a subcircuit. Okay. The dot subcircuit option allows you to initiate a subcircuit that can be modified when called in the SPICE deck. And the notation for it is you have your subcircuit, you name the circuit, so if we're doing inverter, we do I and V. Inputs and outputs, so we could call A and Y, just like we did before. And then we have variables that we're going to define afterwards. And then next, inside the circuit, you're actually going to define what you want it to do. So we would take that code that we had from last time and then relate it to the input variables. And then instead of .end, we want to use .ends, E-N-D-S. Because what will happen if you put .end there?
Your program ends early?
Yep, program ends early. It's like putting a return 0 in the middle of your C code. So while you're doing that, let's see if I can, this is an example of a circuit inverter. Let me zoom in and I can let you guys copy. For those of you who weren't in class last time, remember these are the ones you can type and you include on your lab report, so you don't have to furiously scramble to write. But basically, we do our .subcircuit command. We have called it INV. We have our input and output. And here our two variables are going to be N and P. So N we call that for NMOS, and P we call that for PMOS. So our base case, which is what we're doing here, we're establishing a base case, and then we can overwrite it like a constructor when we call it later, is that N equals 4 and P equals to 8. So here, what's going to happen is we're going to define our NMOS transistor. We have input, output, ground, so drain, gate, source, body, CMOS, N. W is equal to N, so this becomes 4, and L becomes 2. And then for PMOS, drain, gate, VDD, VDD, source, body, CMOS, P. W is equal to P. L equals 2. And then we do our various forms, and we could, as we learned in the table last lecture, this is how you relate back to those area and perimeter source delays. So going back here, what we can then do is we're going to actually, we can put the subcircuit into the SPICE deck first, and then because we're doing a fan out of 4 inverter where we have 5 inverters, we just call 5 inverters, and instead of having to rewrite every single time, what we're going to do is we're just going to put the widths and lengths that we want as the P and N values. So that automatically will, when it compiles, it's going to automatically take your circuit definition, take those values, and put it in there for you. So this should reduce your amount of time. If you're doing things with thousands and millions of transistors, and they all go to the same technology file, and you're using a design automation, instead of having to rewrite the circuit definition over and over and over and over again, you can just use your subcircuit and include smaller files. And this is when you build cells, this becomes very important and useful. And so we're also going to find something called a global command, which allocates nodes to be referenced within subcircuits. So this becomes important because if you are actually trying to, let's see, so I have a dot global here. Okay, dot global, VDD, and ground. Inside the subcircuit, the VDD and ground in the subcircuit is the same as the VDD and ground in the overall circuit. Does that make sense why that's important? Because if you don't have a dot global command, what will actually happen is it will just localize it, and then you'd have to include VDD and ground as your inputs, which means every time, we had the P and N, you'd have to have VDD and ground as your global variables instead of local. So you can use this dot global to save yourself a lot of coding and time.
Would there be an instance where you wouldn't want to do that?
Whenever you would have an instance where you just want it to be, okay, so this is a really good question. Let me draw out an instance. So you have your VDD and ground for your inverter, which is what you'd want to do. For AND gates, you're going to have your PMOS, right? And you're going to have your output, and you're going to have your NMOS, right? So that's a 2-input AND gate that's still normal. What we have, remember we had the instance, I'm trying to think exactly how it's drawn up, but we did a number of different NAND gates where we had, or 6-input NAND gates or 8-input NAND gates, where you could design them in different ways. If you wanted to use 6-input NAND gates, you'd have intermediate nodes in between all of them. The intermediate nodes are going to be local to the subcircuit. But for, let's say for some reason, you decide one of the intermediate nodes needs to drive something else. Then you'd want the intermediate node to be part of your variable, so that way you could then you could use that intermediate node to drive the output. Did I answer your question, Tanner?
Yeah.
All right, good. Does anybody else have any other questions before I go over the specifics of this SPICE deck? Okay. So I call this fan out of 4 inverter. Our supply voltage parameter is 1.0. I've also defined this parameter H equals 4, because if we initially have 8 and 4, right? So this can be, I'm sorry, that's 2 and that's 1. So that can be H times 2, H times 4. So if you're, the reason why this becomes useful is if we go back to our circuits, you see that they're all multiples of 4, and that they all increase. So this, this 2 and 1 is actually going to be 8 and 4. This 8 and 4 is going to be 32 and 16, right? And so that's actually going to multiply because we have to relate it back to our 2 lambda. So instead of having to do all these calculations, relating it back to our inputs, because our inputs relate to 8 and 4, we can just use a parameter times 4 to be able to relate that back here. So here we have 4 and 8, and then you just use double multiply. That's how using that parameter helps out. So then one thing I should say here, because of that, when you did your calculations in class, those are the numbers you're going to come up with. But then you'd have to multiply everything by 4 in order to make it work. So what you can do is you can just define this parameter h equals 4, and then multiply it by the values you came up with in class, and you don't need to do any additional multiplication. You just code it in there for you. And so, again, when you're doing millions and millions of transistors for a design automation project, using this parameter to multiply the values you get, the values of your multiply are then put into your algorithm, which are then put in to generate your SPICE file. So then you don't need to add another step of conversion. So we have our supply voltage or parameter, our scale, which is going to be half lambda. We've included our library. We have our temperature, and we include adoption.post. So that way down here, we talk about, we're going to get to this in a second, but we have a .end file. But here, what we've done is we've defined our VDD and ground. We have our supply voltage. So as you have single quote, SUPPLY, end quote. So anytime you're using these parameters and you define them, you put them in single quotes to make it work. So then what we've done is we have VN is A and ground, right? So that's our supply. We've defined a pulse here. Here we have properly accounted for some sort of delay time. And we have our full 280 picosecond cycle, and it's high. So it's 20 picoseconds rise, 120 picoseconds high, 20 picoseconds fall, 120 picoseconds low. And that's going to keep repeating until the end of our transient analysis. So this was 280 picoseconds per cycle. If you recall last time, it was 800 picoseconds for our transient analysis. So this would repeat 3 times and a part of a fourth. It'll just keep cycling until that .tran command ends. Then we've created 5 inverters, A, B, B, C, C, D, D, E, E, F. So F would be that final output. C and D are our values under test, which we're going to learn about next section. But we use these values here to multiply for our P and N inputs. So that now matches our subcircuit definition. And I've commented here, I included this as an example. You're allowed, just like in C, C++, or Java, you could have a command at the end of you could have a comment at the end of a command. So there I've defined all of what each inverter is. So this isn't the end of our file. We're going to be finding certain measurements. And so we need to know these 3 elements when we're going to do any kind of measurement. First is the dot measure, which kind of should intuitively make sense. The measure formally means it's a statement that measures simulation results and prints them to the output file. So you're going to have dot measure, and then you're going to name. So let's say we're doing fall time. We can call it TF. TR is T-rise, top propagation delay. TPDF, TPDR, all of those things that we learned back in section 3. Now we're going to use those to actually measure those in an actual circuit. So in order to do that, we have to define when the measurement starts and when it ends. When it starts, that's when the measurement is triggered. So that we call that all uppercase TRIG. The TRG indicates the value the node should reach in order to trigger the beginning of the measurement. And then we've triggered it, And then when we get to the end, we've reached our target, or TARG. Formally define that as the target indicates the value the node should reach when the end of the measurement is reached. Also, we're going to be using these things called rise and fall. So here's, so if we're measuring rise time, right? So let's say we're going to call this TR. And we're going to do dot measure TR. Well, let's say that our trigger is, typically it's 0.2 of the supply, and the target is 0.8% of the supply, right? So if you don't indicate whether it's a rise and fall, here's what you can get. 0.2 of the supply, all the way up through 0.8 of the supply. So not only have you measured the rise time here, you've also counted the entire time it was low, plus the last 0.2% of the previous fall. So we differentiate between those using rise and fall, meaning that the input value, the node, so let's say this is node C because nodes C and D are the values we're measuring. If we're measuring fall time, we would have D, and it would be trigger would be 0.8 supply fall, and the target would be 0.2% fall. And then rise 1 indicates that it should be measured on the first rise value. So if we had, this would be rise 1, this would be rise 2, this would be fall 1, this would be fall 2. Does that make sense? Okay. So here is a sample stimulus code. So here we have 280 because we want to measure one full cycle, and I've set it to 0.1 picoseconds for our measuring increments. Next, we're going to call this TPDR. We're going to measure the time of the propagation delay of the rise. We're going to trigger at node C, because that's our input. Supply over 2, so here, this is actually measuring, it gets here, and then D is going to start falling, because it's an inverter, right? So from the moment it hits half of the supply on the rise, to the moment it hits half of the supply on the fall, is our TBDR value, and that's going to measure, we're going to measure that. So remember, these pluses are concatenated onto a previous command. So this first command is measuring the propagation delay of a rise by triggering on the input, the fall, to the output of the rise. So that delay is how long it's going to take for us to rise. And recall, if we don't properly measure the PMOS and NMOS, then you're going to have different propagation delays for rise and fall. So the second command, we want to actually measure the fall time. So you can zoom in here. So we have our rise. So if we have our rise delay measurement, what should we have dot measure TPDF? What should this command be? So we're measuring the propagation delay rise. We're just writing this again, except for we're measuring the fall propagation delay on the output. Switch them. Switch. What in particular about it?
The fall and the rise.
The fall and the rise. So why is that? Tanner, you are correct, but why is that everybody else? It's kind of. Why is Tanner right? You're on the right track. So basically, you're measuring from the fall on the input to the rise on the output. That is our propagation delay fall. So you can just switch these around for C and D. And the appropriate detail, and this is why I wanted to go through this, you trigger at the input node, because we have the unit under test as the third inverter, right? So the input node of the third inverter is C. And specifically, it's V of C. Meaning we're measuring the voltage. We're not measuring the current, which would be I of C. This would be V of D to measure those different values. So see, Tanner is in fact correct. We have our supply, and so if we want to measure our propagation delay, what we do is we can do this where we have our single quotes and we define a new parameter, and that value is equal to our measured rise time plus our measured fall time divided by 2. So it's just the average. So we did all those calculations back in section 2 to try to make the rise time and the fall time the same, right? So if you've properly designed your inverter, you should be able to measure rise time, propagation fall time, and total propagation, and these three values should be very, very, very similar. When you're getting to like, 10 or 11 decimal places which you can regulate in your simulation, you're going to get very small differences just because they're holes in electrons. But generally, they're going to be very similar. And now we can measure rise and fall time, or I kind of alluded on how to actually do this. Rise time is both of them are output. Your trigger value is equal to 0.2 supply of rise, and target V of D, the value is 0.8 times supply times rise. You use the single quotes here. And then for the fall, you trigger at fall here from 0.8 to 0.2. And these are V of D because that's the output node of that particular found out of a particular inverter. So this is the actual response when you actually run the simulation, just to keep the good fundamental .end there because we used option.post. So here, this is actually a simulation of all of our nodes. So here, this is kind of our A and B, right? A and B is this ... and so forth. C is this one. So we've shaped our input here. So we have some sort of delay because of our A and B inputs, and that comes here, right? So C, and then we would be measuring, and then D is this one. We have a little slight bump there because it's not perfect because we haven't properly optimized our circuit. And then we have a long fall delay. Again, D is here. And based on those, we can actually measure our rise delay and fall delay. We notice they're slightly different because they're not optimized. The fall time propagation delay is 16 picoseconds, and the propagation delay fall time is 18 picoseconds. So you can actually use the SPICE deck. Now, up to this point through section 1 through section 6, we've learned kind of our theoretical optimal circuit. Now we're actually going to be going into code and actually running it to make sure it actually works. And so now I've put the entire code together. And so that's, you guys have now written this SPICE deck. This should all make sense by now. Does anybody have any questions about this? I'll gladly go through this SPICE deck again if you need any explanation on what the purpose of any command is.
What's a good place to get like a command list? Because that right there is pretty much all we need.
Oh, no, we're going to go into more. I can actually send you guys a link that has a good description of everything in SPICE. It is about 600 pages long. I did dig through it. I do feel that SPICE is kind of under-taught in CMOS courses, so now this is the most comprehensive CMOS lecture out there. But what you can do is you go in there and, if you don't mind if I scroll, I know you guys get irritated about that in the videos, but a lot of this comes straight from that. Like these simulation waveforms come from this document. Here, I specifically, we're going to be going over something called Monte Carlo analysis. Yep. You guys are familiar with Monte Carlo analysis? Of course. Okay. Let me go back here. So this is where we're at now. So anyway, that's kind of, I've taken I've combined things from the textbooks and a couple sources plus the HSpice guide, which I can email to you guys if you want to look into further. Yes, Kevin?
There's a SPICE quick reference on Stanford's website.
Let me see which one you're talking about. Yeah, don't refer to that.
Okay.
If you refer to, if you're, that's for like people who've been taught and they know what they're doing. If you're, as people who are new to this, if you read that specific thing, it will confuse you. It'll hurt more than helps. I've seen people use that many. It's 2010 or 2011, right? That thing's been around for a few years.
Yeah.
Yeah. So anyway, so I'll send you guys the list out there anytime you encounter something new, or whenever I describe a command like a dot measure command or Gaussian for Monte Carlo analysis. Right? It will go into a tremendous amount of detail about how the command works, what you're expecting to do. It'll give you some code samples, and we'll actually show you an example of an actual simulation. In the lab, which I'm going to post the first one on Thursday, basically just go step by step with what I'm doing, and it'll work. So, but does anybody have any questions on this specific thing we just did with the inverters?
So we're just gonna write this. This doesn't really have to do with anything in the code, but we write this code in WinSpice, or do we?
Yeah.
Okay.
Mm-hmm. WinSpice is a Spice compiler.
I don't know if we need like Notepad or.
No, you can. No, you can. There'll be a couple of times when you can use Notepad, but you can. WinSpice has its own. You can render it in Notepad++ or Notepad, and then you can run the command in there, and you can do all of that in there. So. Any other questions?
Again, not really for this code, but how much do you want us to comment? Just enough for us, or enough to know that we know, or?
That's a good rule of thumb. Enough to know that I know that you know what you're doing. So one of the things, one of the feedbacks, particularly from the students who took 385 last year, trying to teach better coding principles, and one of the things I consider very important is commenting. This is how I've added comments to the code you'll find in the book, just to kind of show you if you got this code randomly. Let's say I was the project guy, and we're working at AMD or Intel somewhere, and I've written up some Spice code, and then I have now become a professor at the University of Mississippi. Bye, suckers, right? And you are the person who has to take my code and run with it. You want me to code comment like this, right? If I took this all out and just a bunch of Spice.
Top comment, good luck.
Yeah. just star lol. Okay. Does anybody else have any other questions on this before we continue? All right. So, up to this point, we've kind of put a circuit in there and let it run. So, this concept of circuit optimization is we've kind of assumed these PN ratios, right? But as you start putting circuits together, you're going to notice that they're slightly off. And what you want to do is you want to avoid this whole idea of simulate and tweak. I think I've hopefully said this enough. You guys won't be doing that in your projects. Do not simulate and tweak. Use these, troubleshooting concepts. Use your you want to use certain tools to be able to figure it out. So here I'm giving you another one. We're going to be doing these circuit optimization where we're actually going to figure out what PN ratio gives equal delays. So we have our TPD, our delay fall, and our delay rise, right? So what we're going to try to do is we're going to try to figure out measurements in order to make those the same. Because in the previous one I presented, there was 18 picoseconds and 16 picoseconds. We don't want that in our circuit. We want them to be as close as humanly possible. So here we've defined these, right? So except we're going to do something a little different. We're going to define an optimization where we want to come up with our optimal PMOS widths in order to make these rise and falls the same. And here, P1, 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 we're going to be finding the optimal range to make this actually work, to make the rise and fall times the same. And so we're going to be using these three commands. First, we have an opt range function, which allows us to initiate a dot param value we will perform a transient analysis on. Pick P1 there. The format is initial guess, lower bound, and upper bound. The initial guess is kind of what we've learned up to this point in this course. We know that it should be this, should be between some range, and our initial guess is what we've calculated for the ideal value. The dot model allows you to specify the parameters of a variety of devices. And specifically, when in this example, we're going to go over here in a minute, we're going to use it to try to use a maximum of 30 iterations. So we have our high row best guess, and we're going to try to optimize it by taking a series of guesses in between. So that opt model, opt range function is going to use an algorithm here to be able to actually figure out the actual value. So the goal command, which is down here, our goal should be that the difference between the propagation delay should be 0. That's our goal. You simulate it, it's not 0, you haven't made your goal. The moment you hit 0, it's like while goal does not equal 0, while differences keep going, but the moment you hit it, you're kind of creating a while loop in there. So you have your optimization set up, and here is what we're doing. So we have defined our parameter, and we use the opt range function, where our initial guess is 8, and our range is from 4 to 16. We're going to model, we're going to call it opt mod, and we're going to be number of iterations on the optimization is 30. So what this code means is we're defining our opt mod, and we're doing it somewhere between 4 and 16, 30 times. And the closest we get will be the optimized value. So again, we have done our transient analysis, except we're doing a sweep. We're optimizing opt range. And the results are diff. Diff is what we define down here. Difference is the parameter propagation delay rise minus propagation delay fall. We've set our goal to be equal to 0. To the average propagation delay, that shouldn't, that's bad code. It should be equal to TPD. The goal should be that. So this should be TPDR. Yeah, that is incorrect code. So here, just like before, we've done our triggers for TPDR and TPDF. Here our goal would just be, we want them to be the same. And so we optimize the values based on the number of iterations we do. So then what happens, what this code is doing, we're running our inverters. We select what the p-value should be. We are checking our different results. The reason we set it to diff is because we can then pick 2 measurements and set goals, but this one will be, if we meet this one first, that'll be our ideal. Then model, opt mode, we do it 30 times. So now we've followed the sweep. We have our function, we have when we're stopping, and the number of times we're doing it. And then, as always, .end. So then these are the values that kind of came out based on the textbook. The PN delay ratio is actually 2.9 to 1. And here it was, the delay was 17.9 picoseconds, which is actually slower. Then because we had 18 picoseconds and 16 picoseconds, so we ended up having a slower delay. It was very close to our. So what happened is we ended up raising the ratio from 2 to 1 to 3 to 1 and slowed our circuit down. So as we also mentioned here, we've made our PMOS really big. PMOS is the leading factor in power consumption of the circuit. So we want to figure out what's our lowest average delay. We've run this optimization. We don't like what we want, so now we're going to pick a different optimized circuit. And this, if for those who remember the 4 design principles, this is good design requires good compromise. So now we've replaced the transient value, 1,000 picoseconds. We've optimized op range, results TPD. So now we're trying to find the best one there. So we've changed that from our difference to TPD. So now we're finding the lowest optimal range. And then here we got, oh, you know what? Now I know what we did. This is actually correct code. And let me explain why. This goal equals 0. Now I know what I was doing. Here we want to give the lowest average delay, right? So what's the lowest average delay you could possibly want?
0.
We want it to be 0, right? So here we set it, given our goal of 0, it's never going to actually reach 0, but the average that's closest to 0 will give us the ratio, the PN ratio that we want. So then these are the values that are PN ratio of 1.8 to 1. As you can see, the average delay propagation, these end up being different. So if you want them to be exactly the same, this circuit, if you want it to be the lowest average, you're going to have a significantly lower fall time than rise time. Right, so now there are ways to, kind of a brief way of measuring power. You just pick your node. You say print VDD, so this is going to print it to the output and measure power, average power. And there you can actually measure power ranges. And where this becomes useful is if you're doing a design automation and you know where your rise and fall is going to be, you can measure dynamic power consumption. Or you can measure average power consumption or static power consumption based on the different times. So you can actually, if you're writing some C code or C++ code to generate SPICE, and you, as part of the process, you actually know where your rise is going to be generated, where your fall is going to be generated on every loop. You can use that to then measure the power that's going to happen every time. So that's when you're going back to my dissertation, like I was talking about before, measuring those power spikes. Those power spikes occur during rise and fall. When there's nothing going on, there's no power spike. So if your goal is to do 256 of your S box, and you have 256 different input combinations, and you have to measure the power consumed during every spike for the circuit, that's how you would do this for a specific time. So I kind of, before I go into Monte Carlo analysis, I kind of want to briefly talk about these device models a little more. So the first one is called SPICE Level 1, and it basically based it off of what's known as a Shockley model. You know the Shockley model is this. You've seen this before many times. So then what's going to happen is, and here's the TGO of 25 is just this. This should be 26. I've screwed up the numbers. I'll fix them. These values here, Kp is beta, WEF, LF. Now those values are all going to be in your model. Lambda times VDS. So VGS, VTS over 2. So these are kind of more optimized values. You can have 1 plus lambda for your PMOS and NMOS to try to calculate your VDS. So these actual big lambda values here are the actual, and this is where I'll cut it off. So VGS is what you're putting into the circuit. Your lambda, WEF, KP, KP over 2. Remember, you have mobility over 2. All this together. W effective, L effective. KP is your mu times your oxide thickness times your oxide permittivity. So all those values are calculated in this level 1 to be able to correlate to the Shockley model. And also from our body effect, initial threshold voltage, you have gamma, phi, VSB, and then your phi again. So that's the TGO there. That should be 26 and 27. I'll fix all of these. But the way it was written out before, you would include a dot model command before you have a dot include. So if you recall, you would just call it the model NMOS, and it's representing an NMOS circuit. You call it level 1. You have your oxide thickness. You have your mu EOX, TOX, or KP. Lambda is 0.2. Initial threshold voltage, your phi, your gamma values, and then you have your junction capacitances. And you can use all that to write a model in there based on, and you pretty much every single one of these values you've calculated at some point in class. So you can actually create your own level 1 model at this point. So basically, now that the model that you guys saw earlier last class is huge. Now we're adding all kinds of different physical levels. Levels 2 and 3 added effects of velocity saturation, mobility degradation, subthreshold conduction, and drain-induced barrier lowering. So now you kind of learned very briefly about all that, and then there's this whole, each one of those is its own separate field of physics, and all of those values are then put into your level 2 and level 3. Level 3 model is based on empirical equations that provide similar accuracy, faster simulation times, and better convergence. So your convergence, for example, we did a very brief example of that just now, trying to make our rise time and fall time the same. And however, these models still do not provide good fits to the measured IV characteristics of modern transistors. So now we're getting smaller and smaller. One of the trade-offs, getting smaller and smaller, you have to worry about the physics more and more and more. If it's really big, it kind of relates to how you're just turning it on and off. But as you get smaller and smaller, you have all of these different physical things that you have to consider. And the BSM, which is you saw an example of a BSM3 model. The Berkeley short channel 8-FET model is a very elaborate model now widely used in circuit simulation. The models are derived from the underlying device physics. So the TGO ends here. This actually 28, 29. When I post the actual what the TGO is, you should be able to read it. So now we can use all these things that we're talking about before. Multiple gate capacitance models for different PMOS and NMOS transistors. Diffusion capacitance resistance models. Gate leakage. Now that we're getting smaller and smaller, and BSM4, 4 is just the version number, you now have to worry about punch through, gate leakage, capacitance, detailed threshold voltage model, including body effect and drain-induced barrier lowering. So our model levels 1, 2, and 3 didn't really account for dibble. Now we are, and now we're accounting for all these short channel effects and sensitivity parameters such as threshold voltage, transistor width. We learned earlier in class that you make the transistor length longer or make it shorter, that it has an impact on the ability to create a channel, which is what our threshold voltage is. All right, so the last thing I want to go over, seems like you guys have already been tortured by this concept before, of Monte Carlo simulation. So we're going to have these random variations on the circuit, which is our definition. So here we have our normal operation, and then we're going to test around all through here. Now, based on what you guys have learned already in class, why would a Monte Carlo simulation be important, especially if you're putting out new chips or a new die?
It's not going to be perfect.
Trying to find out what's going to fail.
Exactly. So we're trying to figure out, we have a whole different range of voltages, temperatures, anything else, in our design corners. And we can pick a design corner, simulate, run a Monte Carlo analysis. What's our range of things that we can expect and still work? So here, you guys probably, I'm going to zoom in so you guys can read this. But basically, you have some sort of expected normal value, right? And we've done the Monte Carlo all over the place, based on our normal and unified distributions and Gaussian distributions. Based on, I'm going to present 4 different ones that we can do. And we want to simulate the effects on circuit performance if it still works. So if we know that we have some sort of circuit that tests out here, and then based on that we figure out that we have terrible rise or fall times, or we aren't able to get consistently to the noise margins, that's when you're going to throw out the chip. Sorry, did somebody had to say something? Okay. So we have the basic syntax. So that's what we just started. We just started about acceptable yield. The basic syntax of a Monte Carlo analysis includes 3 elements. First, defining the parameter of one of the distribution keywords, which we're going to go over here in a minute. Using the parameter in your netlist as a value for an element model parameter. And then we're going to use sweep or Monte in the analysis statement. So first we define what it is we're measuring, and then we're going to use the parameter in the netlist that we're going to measure. So if we're trying to measure power consumption, or we're trying to measure rise and fall time, or we're trying to measure the current based on the different parameter, and then we're going to perform the sweep or the Monte Carlo analysis there. So here's an example. Again, this is kind of Monte. We're going to do 30 different random checks. And there we can add inverter delay simulation to offer a statistical delay. So here, the way if we added this to our previous code, not only could we detect our rise and fall time based on our guesses from our optimization, but then we can add Monte Carlo analysis to it as well. I also wanted to include this very valuable thing I wish I had been taught as an undergrad. This would have saved me a ton of time. The .ic command is an initial condition command. So when you have a feedback loop in your circuit, right, and it ties back to the input, but it's not an input itself, right? So you can't actually set the value by having, like, if you have A, B, if you have some sort of sequential element, you have an output that just ties right back to the input, right? You have A and B. And let's say this is node Q, right? Well, we can't set node Q with inputs because it's not tied to an input itself. So what we can do is do IC V of Q equal to 0. So as I mentioned here, it's particularly useful in simulating sequential circuits. But you can also use it to set your initial condition for anything, especially if you're performing a Monte Carlo analysis. And let me go back up here just a little bit. Okay, so I think that's the last TGO, right? Yep, that's the last TGO. So 7.31. Here's the formats. There are 4 different types of Monte Carlo analysis. We have uniform distribute. Stop it. There you go. So you have your uniform distribution function using relative variation. You have uniform and that's called unif. And everything starts with a dot param. And then the parameter you're measuring, you just put that as XX. That's unif, your nominal value, your relative variation, and then we'll go over these concepts of multipliers here where you're adding things on. So the first one is your uniform distribution using relative variation. When you use absolute variation, it's A unif, so that's the major difference. So you have your nominal value and your absolute variation. Again, it's a unif there. For Gaussian distribution using relative variation, dot param, the measurement, your value equals a Gauss, nominal variation, relative variation, and your sigmas, we're going to be going over sigma. That's part of Gaussian variation. And then the same thing, a Gauss is your absolute variation, your sigmas, and your initial a Gauss here, and the value you're going to be measuring. So we're going to be going over an example of absolute Gaussian variation as an example of a Monte Carlo analysis. So once I go over that, then I'll discuss what I want you guys to have for me and the fun adventure I've had with SemiWiki. I think Thomas is a little privy to it. Okay, so the last thing I want to do here is consider the following example in the simple RC charging circuit. The value R1 is a nominal value of 1K and is varied by 400 ohms. So remember, we have our RC delay model. You can actually use this to measure difference in variance if you actually had a difference in widths of PMOS transistors for 10 iterations. And so here's our circuit where I just put everything together kind of here at the end. This is actually the code that's from the HSpice document that I'm going to send you guys later. So we have our option post. We have defined our absolute uniform distribution, as we've called it resval. And we've defined our voltage source, VSRC1. We have R_1, C_1 node. So we have 1 and 0. We have our voltage, we have our resistor and our capacitor, and they're both tied to ground. So our resvol value is our uniform distribution. So it's initially 1,000 ohms, but it can distributes by, it can be varied by 400 ohms. And we set our initial value of V2, which is here, to 0. We have no value voltage stored on the capacitor. So now we perform our dot tran. Here they actually use 1e-5 and 5e-3. So we have our steps and our total time. Sweep Monte. Remember, we're going to do 4 different tests. And so what we want to do is we're measuring when the time constant. Remember, RC is equal to 0.632. The time constant is equal to 6.32 times RC. So what you're going to be doing is you're measuring the transient TC. We're going to call TC time constant when V2 is equal to 0.632 times, we call it 5 because it's 5 volts. They could have just said time, we could have did a dot param supply is 5. That would also work. So you can combine some concepts there. And then we're going to do this dot probe command, which basically we're measuring voltage 2. And voltage 2, we're actually measuring RC step response. And then we use resvol to perform that measurement. And then dot end. So we're actually probing, like you're taking a physical probe, and you're measuring that actual value. And we'll do worst case in Monte Carlo sweep example next lecture. I'll press